Good morning, everybody. My name is Ulysses Nunez, and I am a PhD student at Georgia Tech under the supervision of Dr. Glenn Lightsey at the Space Systems Design Lab. And today, it is a huge honor to present to you on the topic Sensitivity of Separation Indicators in Spacecraft Formation Collision Risk Analysis. We will start by outlining this presentation. First, we will introduce a specific type of collision risk indicator in spacecraft formation flying, and we will pose a research question for the work in terms of the sensitivity of this indicator to changes in its defining parameter. Next, we will spend some time developing the preliminary notions of collision events and collision probability as we have formulated them. In the theory section, we will set up the sensitivity of our probabilistic indicator of agent separation. Then, we will deal with the computation of probability measures and probability densities via numerical quadrature and Monte Carlo sampling. Finally, we will list the test cases we used and we will present our findings. Let's dive in. Spacecraft formation flying is a set of more than one spacecraft that track dynamic states relative to one another. Having such an arrangement of spacecraft is beneficial because it can endow missions with improved scalability and maintainability. It also has many potential scientific applications such as gravity field recovery, weather forecasting, exoplanet detection, and more. Collision avoidance is a necessity in formation flight because of kinetic threats to any formation, both from external debris and among agents in such formations due to drifting or maneuvering. These threats are constant, therefore, safety concerns must be balanced with wise propellant usage. Work in collision avoidance in formation flight can be broadly categorized into passive and active schemes. Passive schemes focus on the design of passively safe relative orbits, with maneuvers only indirectly addressing collision risk. Active schemes focus on monitoring collision risk, checking safety criteria violation, and, where needed, planning and execution of dedicated collision avoidance maneuvers. This work focuses on active collision avoidance methods, which are characterized by their collision risk indicators. In these charts, you see conceptual illustrations of probability density functions, or PDFs, of the relative position between two agents. One type of collision risk indicator is misdistance, which is any statistical description of the physical separation between two agents, as seen on the left. The other type of collision risk indicator is the probability of collision, which is the probability mass of the relative position which is inside of a collision region. Collision risk is mitigated by setting constraints in an optimal control problem in terms of these indicators. Previously, we the authors proposed an indicator of physical separation that has a probabilistic interpretation. This is one way to weave together both types of collision risk indicators. Let's define P through sigma as a constant with approximate value of 0.27%. Then, the 99.73% minimum distance, or rho through sigma, is defined as the P through sigma percentile of the distribution of the norm of relative position. Since there is a stochastic description for the relative position, the norm also has a stochastic description. Let's define the kpc as the instantaneous probability of collision and the joint hard-body radius as a minimum safe inter-spacecraft keep-out distance. For two spacecraft, we have proposed that rho 3 sigma is a collision risk boundary in the following way. If the joint hard-body radius is less than rho 3 sigma, then the kpc is less than p 3 sigma. And if the hard-body radius is greater than rho 3 sigma, then the kpc is greater than p 3 sigma. The main research question that we wish to investigate is whether this interpretation of rho 3 sigma holds in practice. Specifically, we are concerned with the regularity of rho 3 sigma. That is, if small variations in p 3 sigma result in correspondingly small changes to rho 3 sigma. Even though p 3 sigma is a constant, numerically there will be errors in checking whether the cumulative distribution function, or CDF, of the norm of the relative position evaluated at rho 3 sigma is equal to p 3 sigma. We can think of these probability differences as effectively changing the value of p 3 sigma that defines rho 3 sigma. Naturally, if the regularity property holds, then estimates of rho 3 sigma do have the same interpretation as the true values, to within some acceptable tolerance, and it can reasonably be expected that estimates of rho 3 sigma will converge to the true values in the limit. With that in mind, let's dive into the rest of the work. In this work, we employ a stochastic description of the instantaneous relative position between two agents. Specifically, we assume that the relative position is absolutely continuous, which we characterize in the following way. The relative position is an absolutely continuous random variable if and only if the relative position has a probability density function, or PDF. Additionally, this PDF exists and is unique almost everywhere, that is, except possibly within a set of zero measure, and we can compute probability measures in the relative position through integrals of its PDF. This is a consequence of the Radon-Nikodym theorem. Now we will formally define collision events. A characteristic length or hard body radius for some agent I, denoted by Li, is the furthest Euclidean distance from its center of mass to any point in its body, preferably under a worst-case configuration of all appendages and deployables. Then we make the hard body radius assumption, which simply holds that the body of agent I can be approximated by a ball with radius Li centered at the center of mass. This is a conservative assumption that also simplifies the definition of collision events. It should be noted that these balls are surrogates for the size of the object, and they are not position PDFs. With these notions, we define a collision event as the condition when distinct agents occupy portions of the same volume of space at the same time. That is, when their circumscribing balls have a non-empty intersection. Alternatively, a collision occurs when the distance between centers of mass is less than the sum of their hard body radii. Clearly, a buffer-safe distance may be added here and it would still be captured by a joint hard-body radius. So, without loss of generality, a joint hard-body radius may be regarded as the defining parameter for collision events. We define the intersection or collision volume as the region of relative position space in one, two, or three dimensions where the collision event occurs. That is, all points in relative position space whose distance to the origin is less than the joint hard-body radius. Then, we define the kinematic probability of collision, or KPC, as the instantaneous probability of the collision event as previously defined. Since we have assumed absolute continuity of the relative position, the KPC is computed as the integral of the relative position PDF over the intersection volume. More generally, we also define the radial probability measure, denoted by h, as the probability mass that's contained in the set of points at a distance from the origin less than or equal to a fixed constant. Clearly, the radial probability measure evaluated at the joint hard-body radius is equal to the KPC. Therefore, h generalizes the KPC notion by allowing for variable joint hard-body radii. We define R as the norm of the relative position. Clearly, the radial probability measure coincides with the CDF of R. We employ the fact that because the relative position has a PDF, the norm also has a PDF. This is a general result for n-dimensional random vectors and their norms. We did not find such a result in the literature, so we went ahead and proved it, but we are not including it in the paper due to space. This is an important result because it does not assume that the relative position belongs to any particular family of distributions. It will also be helpful for univariate analysis later on. We formally define the 99.73% minimum distance, or ρ3 sigma, as the minimum non-negative scalar such that the CDF of the norm of the relative position evaluated at that scalar is equal to P3 sigma. Under the absolute continuity assumptions we have made, it turns out that ρ3 sigma is the minimum P3 sigma quantile of R. Also, ρ3 sigma exists and is unique. From this definition, we can quantify the sensitivity of ρ3 sigma with respect to its defining parameter p3 sigma via the derivative of the one with respect to the other, which is the reciprocal of the PDF of R evaluated at ρ3 sigma. At this point, the importance of the absolute continuity of R becomes clear. We can only quantify the sensitivity of ρ3 sigma if the PDF of R exists. What this is getting at is whether there is agreement between the PDF and the derivative of the CDF. There are continuous random variables, that is, random variables with a continuous CDF whose CDF is not equal to the integral of its derivative. In those cases, the derivative of the CDF is not really a density function. One of the most notorious examples of this is the Cantor function, or the devil's staircase. However, R is absolutely continuous as we have just discussed. Because of this, we know that the PDF exists almost everywhere, and, where defined, it is precisely equal to the derivative of the CDF. Therefore, our sensitivity analysis is sound, and we can carry it out through this equation that we've listed here. Our computational approach begins as follows. First, we start with a spherical coordinate representation of the relative position, which has the magnitude of the vector and two angular coordinates, y1 and y2, which map locations in the unit square to the unit sphere through the Lambert equal area transform. After performing the transformation of the PDF of the relative position that corresponds to these spherical coordinates, we are able to obtain the PDF of R through marginalization of the angular coordinates. We accomplish this through nested application of the ODE 113 integrator in MATLAB. As for the computation of ρ3 sigma itself, we do that in two ways. The first, which we will call numerical, is another nested layer of ODE 113, where we increase the upper limit of the integral of the PDF of R until the output of the integration hits P3 sigma. The second method for rho 3 sigma computation, which we call sample, is a Monte Carlo estimate of the P3 sigma quantile of R, which is obtained by drawing a sample of the instantaneous relative position distribution, taking the norm of every point in the sample, and then finding the empirical percentage. The sample size is 320 million points, which should afford us approximately 4.4 significant digits of accuracy when checking P3 sigma. Even though the formulation of rho 3 sigma is instantaneous, as in it only depends on the instantaneous uncertainty description based on propagation of statistics of the relative state, we would like to check whether this interpretation of rho 3 sigma holds over extended propagation horizons, because this would allow us to use rho 3 sigma to also predict the risk of future collisions. On the one hand, the numerical method is attractive because its meaning directly follows from the definition of rho 3 sigma. However, there are no convergence guarantees because it is not a symplectic integrator, as in there are no guarantees that it will conserve certain quantities such as the integral over the entire sample space. On the other hand, the Monte Carlo estimate doesn't have as direct an interpretation, but it does have general convergence guarantees that hold in high dimensions. Assuming that both estimates agree reasonably, we can use a hybrid methodology where we first compute rho 3 sigma through a Monte Carlo estimate and then compute the PDF as such rho 3 sigma through ODE 113. We have two main results, one methodological result which shows that the hybrid approach for computing the PDF of R at rho 3 sigma is valid, and a more substantive result which shows that rho 3 sigma is, in fact, regular, at least under the examples we consider. We will examine these results for relative dynamic states subject to Cohesi-Wiltshire or CW dynamics that have normal prior distribution. The cases considered encompass a wide variety of closed CW relative orbits, with and without cross-track motion, and, out of the cases with cross-track motion, we are considering cases where the radial and cross-track motion are both in and out of phase. The specific values of the initial expected relative state as well as the initial relative state covariance were chosen because, in previous work, rho 3 sigma and the KPC are related to one another intuitively. That is, one increases while the other decreases, and vice versa. First, although we won't spend very much time on this, we do find that there is reasonable agreement between the numerical and sample estimates of rho 3 sigma, at least within a limited time horizon. We use several arguments to conclude that the sample estimate of rho 3 sigma should be interpreted as an acceptable estimate of the true value over the entire propagation horizon of two orbit periods. Some of the reasons include Monte Carlo convergence guarantees, second-order effects, and completeness of continuous and bounded function spaces. This validates the hybrid approach to rho 3 sigma computation. For more details, please refer to the paper. We will now address the sensitivity of rho 3 sigma. We start by computing the derivative of rho 3 sigma with respect to its defining parameter, P3 sigma, through our hybrid approach. The outcome is in units of kilometers per probability unit, because this is a derivative of a physical distance with respect to probability. We then obtain a first-order estimate of changes to rho 3 sigma caused by small changes in P3 sigma, specifically a change of 0.01%. Hence, the chart shown here is just the previous chart multiplied by 0.01%. We see that the changes in rho 3 sigma for this example are less than 5.1 meters. Now, the relative sensitivity of rho 3 sigma is simply the changes to rho 3 sigma divided by rho 3 sigma itself. Now, we can see the meaning of these results more clearly. The relative change in P3 sigma, which is less than 3.7%, causes changes in rho 3 sigma of no more than 1.88%. Hence, for this example, small changes to P3 sigma cause small changes to rho 3 sigma also. By performing the sensitivity analysis on the rest of the examples, we find a similar conclusion as before, namely that a relative change in P3 sigma of less than 3.7% caused changes in rho 3 sigma of no more than 1.9% for all cases considered, which is noteworthy because they include several distinct relative orbit regimes. In conclusion, Our results answer the question whether small changes in P3 sigma cause small changes in rho 3 sigma, and the answer is yes. Therefore, the percentile interpretation of rho 3 sigma holds under small variations to P3 sigma. This implies that rho 3 sigma can be correctly interpreted as a collision risk boundary in relative position space with probabilistic interpretation, and that this interpretation holds under statistical estimator errors to within some acceptable user tolerance. Therefore, we conclude that rho 3 sigma should be implemented in the practice of spacecraft formation flying as both a metric and measure in the quantification and management of collision risk. Thank you all so much for watching this presentation, and I look forward to your questions.